Okay, so I am Stéphane Zaleski. I'm a professor here at Sorbonne Université, and also the advisor, one of the two advisors of Yash.
I am Sébastien Tanguy. I am an associate professor at the Toulouse University.
Yes, I guess I came from the math department at the University of Bristol.
So David Quéré from PMMH.
Shervin Bagheri from PTH in Stockholm.
Stéphane Popinet from D'Alembert, and I'm the second advisor of Yash.
So now it's your turn. So you have 45 minutes. Tell us what you did, then you ask questions.
Okay, so hello everyone. I am Yash Kulkarni and I am a PhD student at Institut Jean Leron d'Alembert, and thanks for coming to my PhD defense. So these are some planned scientific manuscripts from my PhD. Some are published, some are submitted, and some are in revision. So my thesis will be the dynamic contact lines. Now, it's natural to ask that why we study contact lines. The obvious reason is that for our scientific curiosity, like we are interested what happens here at this three-phase contact line when it is moving, especially, which will be the focus. And on applications part, this has many applications to all kinds of coating processes. For example, in our lenses, this is a typical ad of this optical store where you have coatings on lens to make it UV resistant, or a super hydrophilic coating to make it water repellent, and then on industrial scale coatings, for example, what Kodak does. And we also have applications in pharma industries where you need to coat the capsules and coat some biocompounds, and also it has applications in nuclear reactors because nucleate boiling that is used for cooling that is there, and also coating, doing some protective coating, studying this dynamic contact line is crucial. Let's have some preliminary remarks on the contact line. In case of static contact line, we know that it is well understood in terms of this famous Young's law, where this theta E is the equilibrium contact angle, and this law can be derived from energetic balance. And here I have some screenshots of the original paper of Thomas Young from 1804, and in this paper this equation doesn't appear, but from the essay of Dr. Young you can conclude how this law is derived. And there is also one very interesting thing in this essay of Dr. Young is that he also has variation of surface tension with temperature, and also measured to some extent in form of some grains and how much capillary rise will happen. And of course this equation was independently derived around similar time by Laplace. So I have a photo of Laplace as well. However, when the contact line moves, then we know from the traditional no-slip boundary condition, we have a divergence in shear stress and also the force. So if we write the stress at this fluid-solid interface, at the fluid-solid contact, and we try to integrate it up to the contact line, then we will see that at the contact line, if this goes to that 0, then we will see this force diverges logarithmically. That means we would need infinite amount of force to move the contact line, and this was put in a funny manner by Hu, Shun and Scriven, that an infinite amount of force means that even Heracles, who is supposed to be quite strong, could not sink a solid. So that's how this no slip boundary condition is wrong. And there are multiple ways to regularize this singularity. One way is to allow fluid to have a small slip at the fluid solid surface, which is the Navier slip model, which we will discuss. So we use free code basilisk to do simulations, and here we implement the Navier slip boundary condition. So you can see in the no slip, the fluid solid slip velocity is 0, but here we allow fluid to slip slightly on solid. This slip is quantified by the slip length lambda, which is typically of the order of nanometers, And the way we implement it numerically is by giving the value in the ghost cell layer based on the discretized version of this equation, of this boundary condition. And for this implementation to work, we need to have our grid size delta to be much smaller than the slip length lambda, so that we will control the slip lambda. Now coming back to the problem of wetting, for which we are doing all this, you can imagine that you are pushing down a solid plate into the liquid bath. So if you push it slowly, it will wet perfectly. However, if you push it, there exists a critical speed such that if you push this plate into the liquid bath a little bit faster than that critical speed, then you will see wetting failure and transition to air entrainment, and I mean this air films and these kind of stuff will get entrained, which would eventually degrade the quality of of the coated product. And hence in practical applications, we would like to always operate in a stable regime. The setup we will be studying is slightly different one. This is the curtain coating setup. Why we are studying this setup is because in this setup we can have rapidly advancing contact line. The steady state velocity beyond which wetting failure, the critical velocity beyond which wetting failure happens, is quite large for curtain coating compared to the plunging plate. And in this curtain coating setup, we have a liquid falling from the top with some velocity v, and this solid which is moving from left to right and with some velocity u. And in a steady state, we see that the contact line, a dynamic contact line, which is steady in lab frame of reference, but this solid is moving, so it's a dynamic contact line that appears. And this setup has some very interesting properties. One of the property is that the U critical beyond which wetting failure happens, that depends also on this V, which is the feed flow, which is we are giving from few centimeters high. And also this angle theta d that was measured at the experimental resolution, typically 20 microns, depends on not only U but also on V. So this angle depends both on U and V at experimental scales. And one very interesting thing here is that at experimental scales, again around 20 microns, the flow around the contact line appears to accelerate as it entrains the contact line. So as you approach the contact line, the fluid velocity increases at of course at the experimental resolution. So we will ask two fundamental questions here, that can we predict this transition from steady state to wetting failure up to the experimental accuracy, and then what explains the accelerating flow field around the contact line at the experimental resolution, which is typically 20 microns. So this is our numerical setup. We have a solid plate moving from left to right and liquid falling with some velocity v. And what we can do is we define a capillary number based on this solid velocity u, and we define a Reynolds number based on this vertical velocity v. There is gravity also, but so there will be a bond number as well, but we keep it constant, so we only work with this Reynolds and capillary. And we assume we actually numerically we impose a constant contact angle at the grid scale, which is this theta small m is constant. And since we impose it around 90 degrees, you can see that there would be an appearance of the inflection point, because here the concavity of the surface is changing. So we have an inflection point getting formed, and we will be using Navier slip boundary condition to have steady state cases. Now, another important thing here is that to predict transition from a steady state to wetting failure, gas phase is necessary. If we don't have gas phase, then all values of U in Navier slip would be a steady state solution. There won't be an onset of wetting failure. So the gas phase is necessary to have that transition, and hence we solve full 2D two-phase Navier-Stokes equation. So we automatically have air stresses in our model. Now here are some movies for a case where Reynolds, which is the top velocity 24 and capillary 2.1, you can see the adaptive mesh refinement that we have. And this is one example of how refined the simulation is. So you can see here the curtain has, it has reached a steady state, and we zoom it in 8 times, then again 4 times from this, and then again 8 times, then you see this contact line. So the contact angle that we have imposed is 90 degree, and this is the smallest cell size. So this basilisk level 16 means that the ratio of the entire domain size with this smallest cell size is 2 to the power 16. So we have a huge refinement because we have to resolve this contact line. And this is the stability window that we find. Now we did it for reduced curtain setup. By reduced curtain setup, I mean that this height from which liquid is falling is 1 centimeter, slightly less than what was there in experiment, and the slip length is quite large, which is 10 microns. We will reduce it, and you will see that this was done so that we can compare against previous simulations by Liu, Vandre and Kumar group, and you can see that we have obtained a stability window which is close to their work, and in this stability window, if you are on this blue region, then steady state stable solutions are possible. However, here there was no perfect wetting, so here we have wetting failure. And this phenomena, that if you, let's say we are at capillary 1.5, then for small Reynolds number this was failing. What you can do is you can increase the feed flow rate from the top, and you can delay this wetting failure. So if you increase the feed flow rate, we are here, and then you see that wetting failure is delayed. So this effect is called hydrodynamic assist, because it is somehow assisting the flow to wet the solid. And typically we see 3 types of bump shapes here. If we are at low Reynolds number, we have a bead pulling kind of setup. If we have very high Reynolds number, we get this heel formation, and this heel has some stability issues that we won't discuss. But if you are at a right combination of Reynolds and capillary, then we get a right beneath the curtain combination, which is around the which is often seen to be around the optimum. And here is one example of an unsteady case, how we see it in numerics. So in numerics, what we have is we entrain an air film. Of course, this film is not resolved, but this film that we have entrained marks that this has done the transition to wetting failure. Now, if we look at a steady state solution, a steady state simulation, and we plot curvature as a function of distance from the contact line, then we see that the curvature diverges logarithmically. So here lambda is the slip length, the non-dimensional slip length, non-dimensionalized with the coated film thickness, and R inf is the inflection point distance, and this R is the distance from the contact line. So as we approach the contact line, the curvature diverges. However, and this is a well-known fact in Navier slip model. However, this divergence is logarithmic, so it's an integrable singularity, and we could have steady state solution, but this divergence in curvature implies that pressure at the contact line is weakly singular in Navier slip model. Now coming to our second question, that this issue of this accelerating flow field. So this was brought up by Yuliy Shikumazayev in the review paper in 2006, where he used experimental measurements from Clark, and also they are widely available in literature by Kissler and by Blake as well for curtain coating, that in experiments what they see is that liquid falls, it obeys a usual plug flow under gravity, then the velocity field slightly increases here, then it decreases because there is a bump. But before entraining into the web, the velocity increases rapidly, so we have an accelerating flow field around here. Here I can find only a black and white image from this paper, but from the captions it's very clear that the flow field around the contact line is accelerating like this. However, slip model predicts that velocity field should decrease up to the contact line. So this is prediction by slip model, this is experimental measurement, but we should be careful, this is done at an experimental resolution which was around 20 microns. So we will try to explain this accelerating flow field next. So we look at our simulation, that what really happens. So in our simulation also, this is colored by the speed, velocity, magnitude. In our simulation also we see this fan which means that the flow is actually accelerating before entering the around the contact line, and only when we zoom in sufficiently, only inside the slip length, the flow decreases, the velocity decreases and reaches to 0. So in our equations, essentially this acceleration is captured. So now we will see why this acceleration happens. Some spring action, and you see this drop getting ejected from this sessile drop, getting atomized and ejecting a tip drop over here, then an extended structure and these type of things here. So this setup was experimentally studied at Fluids and Health Network by Fluids and Health Network. And in experiments, what they did at MIT, they had a spring, a stretched spring, a plate, and the drop placed on this plate. And initially the spring would come down and the drop would atomize. So to mimic that type of process, we performed direct numerical simulations using the basilisk. So on the right hand side you see my simulations, and on the left hand side you see the experiments done by the Fluids and Health Network group of Professor Lydia, Bourouiba. And in this problem, our main focus would be predicting this tip drop size, because we are interested in the drop sizes, then also this pinch off time over here. And we saw that contact line effects earlier in part 1. So we will also see how important these contact line effects are, because they would govern how much this contaminated drop, I mean this is we are doing, because these type of drops could be contaminated and they could spread diseases. So some fluid remains at the foot, and of course there is the secondary atomization of these ligaments. Now all this work is published in this paper, and what you can find in this paper is that this process of atomizing of this tip drop can be modeled nicely by the slender jet model of Eggers and DuPont, and a full description can be found in this paper. Here we also have this slender jet lollipop model developed by Navier and Shen, and this slender jet lollipop model predicts the size of this drop based on a lollipop shape added on top of the slender jet model. And here we have our DNS simulations, and in this image you can see that all these three align perfectly: this DNS simulation, the lollipop model and the experiments. Now we have our simulations validated for this tip drop. So we now ask ourselves, how important are the contact line effects over here? So this is very interesting plot that was seen in experiments, that the apparent contact angle, no matter if you start from a hydrophilic drop or if you start from a 60-degree drop, the apparent contact angle would instantly reach 45-degree or something around 45-degree kind of value. So this means that if we have a constant contact angle model in numerics for initial angle greater than 45-degree, then we would be over predicting the drop size, because we would be imposing some constant contact angle. So that clearly means that constant contact angle would not be the best choice. However, the free angle model that was flow consistent would implicitly should have this behavior. Here we compare both the models. We do direct numerical simulations using the constant contact angle model, and we see, although the time of pinch off is predicted correctly, but we over predict the tip drop size by 10%, and when we use free angle we perform better. This bond number is based on the acceleration of the plate, and of course a very important result of this study is that the bond number is weakly, the tip radius is weakly dependent on bond number, or more or less independent of the bond number in high bond number regime. Now since our tip drop thing is good, we see DNS can also provide us information about this secondary atomization. So in this secondary atomization, what we find that at high bond number, the entire drop size distribution collapses. So not only the tip drop, but this entire distribution can be thought of being independent of the bond number at high bond number regime. Finally, coming back to our original goal of studying disease transmission, what we do now is using our numerics, we put some tracers inside the drop before we make it accelerate. And these tracers could represent some contaminated droplets. For example, these type of this type of fungus, which often causes diseases in this irritations in this asthma patients or patients having preconditions for lungs and blood clotting stuff. This type of fungi is often a spore, a hydrophobic spore. So this will have tendency to sit on the outer surface of this water air drop. So when we put these tracers here, hydrophobic tracers, and we accelerate, what we see is that most of the tracers end up in the tip drop above 90%, even at high bond number, and very few tracers remain at the contaminated surface. So it's like the contaminated surface, initially contaminated surface, gets cleansed off, and this is a perfect example to show the lifting up motion of the contact line or the unrolling motion of the contact line, because this is a receding contact line. Now there are some other bacteria that are relatively they differ quite widely in their buoyancy properties. For example, if you take this bacteria that often causes some problems in crops, and also tomato wilt virus, which causes these tomatoes to go bad, although it doesn't cause diseases in humans, but they affect crops a lot. They differ widely in buoyancy, and they could thus form such stratified layers. And when we put these stratified layers, then we again find out that the pathogens remaining at the top end up at the top. They don't intermix, and not mixing among themselves show that the slender jet model is valid here. Here we have that plot to show some distribution for some bond numbers. So what we conclude is that DNS can capture this ligament rupture well. However, most of the fluid fragmentation we see around also involves sheet rupture. For example, here there is a small video of a person sneezing, which was also done by Lydia Bourouiba, and you can see that the sneeze actually goes so far, 7 to 8 meters, which is a huge distance, and this process involves both ligament rupture, sheet rupture, and all kinds of atomization. Now, why this sheet rupture happens, that exact reason is not perfectly known, but we have we know some causes. We know some causes that why this sheet rupture happens above molecular scales, that is above reaching this nanometric size or small size where van der Waal and other things become important. Before that, at micron scale, they could rupture because of presence of some oil droplets, impurities like oil droplets. For example, in this image, you have many sheet rupture happening because of these type of impurities. Also tiny particles inside the fluid, or some bubbles inside the fluid, or there is one speculation that a warm turbulent puff could impact a thinning sheet and cause Marangoni stresses that would cause it to rupture, and there could be some other causes, but we see that sheet rupture often happens above the molecular scales because of some of these factors. So we ask ourselves that can we thus obtain statistical convergence which has both the sheet rupture, this ligament rupture, and large scale atomization? That brings us to the final thing of the thesis, where we study the atomizing pulse jet. Now in this problem, we solve full 3D Navier-Stokes equation, 3D two-phase Navier-Stokes equation with surface tension. We don't have a turbulence modeling, we do full direct numerical simulations. The Weber number based on the liquid and Reynolds number also based on the liquid, they are moderately high. Density ratio and viscosity ratio is also relatively, I mean, this will be in numerics, this will be called as high. And we inject fluid with a pulsating velocity. These pulsations are given to trigger the atomization, so that the sheet ruptures and ligaments and drops, these we will be studying. Now before we study, let's see the effect, I mean how resolution has increased over the years. There is a very nice plot that you can see here, that the resolution, that is number of grid points per diameter, they sort of double every 2.5 years. That also means that the Weber number based on the grid size is decreasing, which is a good thing. And we are here in this presentation. So this, to our knowledge, to best of our knowledge, are the highest refined simulations of this kind of atomizing pulse jet. And we, thanks to the supercomputing grant of at TGCC IRENE Rome, that allowed us to reach up to 34 trillion point effective resolution. Of course, we have adaptive mesh refinement, but this is 34 trillion grid points in the entire simulation and effective resolution of that nature. Now, even with this high resolution, when we did the simulations, these are some results from the simulation. So again, level M that we saw in 2D cases, also here in 3D, level M would represent same thing, that there are 2 to the power M cells in each direction. So total number of cells here would be 8 to the power M. And this also means that level 11 and level 12, the level 12 grid size is half the size of level 11. So we are refining grid in a geometrical progression fashion. Now, as you can see in this plot of the drop size distribution, NS number of drops, these the diameter, and you can see typical bimodal PDF that we bimodal distribution that we see. This is not PDF, but this is a histogram. This has a peak, a larger peak for small drops and another peak for bigger drops, but it has 2 peaks. And this D1 scales with 3 delta. I mean, this is D1 scaling with 3 delta. So D by delta is 3 for this small peak. And for large peak, it scales with 5 by 8. We have a theory for 5 by 8, but we will be focusing here this 3 stuff, that this peak is always 3 times the grid size of that. So what it means is that the drops that are present in this small peak and also in this large peak, they are never converged. They are grid dependent, they keep on shifting as the grid is refined, and this being a constant value implies that even with infinite computational power, we will never get convergence, because they would always keep on shifting to the left. Now, why this is happening? That we found out by diagonizing it by the numerical curvature. So when we colored the interface by the curvature, then what we found, this is colored with UX, but this is colored with the curvature. What we found out is that as weak spot is getting developed, as the sheet is getting thinner and thinner, this height function calculation and all that for curvature causes oscillations in the curvature. So the curvature ripples are found on this sheet thinning on the interface, and these curvature ripples then give rise to this type of numerical ligament network, and then drops that scale with the grid size. So it is this thing that causes the grid dependence. Now we propose a solution for that using the manifold depth method. This manifold depth method is added on the top of volume of fluid method, which was, this manifold depth method was proposed by Leonardo Scherko, where instead of doing an implicit sheet rupture of the WAF, what we do is we make a coarser mesh on top of a finer mesh, and using these signature balls that you can find in this paper, we can rupture the sheet when we want to rupture it at the thickness. We specify the thickness, and then the sheet would be ruptured at that thickness. Here is one example. So this is a 2D case, and here we have detected a thin structure using the signature method of this paper, and we rupture it probabilistically. We rupture it, and you can see here we have artificially ruptured it, not letting, before it reaches the grid size, and these ripples start to oscillate. Now we use this in our full BIC simulation. Here is a comparison. MD WAF is the manifold depth applied to the volume of fluid, and this is usual WAF where you see this ligament network. Now on large scale it looks similar. However, if you see the holes inside the sheets, they are much cleaner than what you get from WOF. These holes here. And when we did the drop size distribution, that is again same thing that we did for usual WOF without manifold depth method, then in WOF with manifold depth method, we see that the converged region, although in default WOF there was a tiny converged region, but now we have a much bigger converged region. So what we have done, we have specified the critical sheet thickness at which we will be punching hole as HC, and then we refine our basilisk level. So we refine the grid and we see a converged region. And when we refine the grid even more, keeping the HC same, we see that this converged drop size, this distribution, that all the drops on right of this DC are converged, that shifts closer to the HC. So this is a good thing that all the drops now for this 15-14 simulation above, after this purple line, on the right of this purple line, have converged. We do this again for a more fine manifold depth level or a smaller critical sheet thickness, and this is the finest simulation, which is the 34 trillion resolution. This one, level 15, basilisk level 15, and a critical sheet thickness at this dash black line. And what we see here is not only that we have a large converged drop size, but the peak, the second peak that was initially moving with the grid, that peak has also converged. This is a no MD case, but this is a case with manifold depth method applied, and we see that even the peak has converged. And here we do the plot for all the simulations that we did, and we see as the grid is refined by keeping this critical sheet thickness constant, the converged drop size range goes towards HC. So that means at very high resolution, all drops above this critical sheet thickness would follow a converged drop size distribution. Now that converged drop size distribution that we get is looks like this. So it's difficult to say whether log normal fits better or gamma fits better, but this is both fit nicely to this distribution that we get, the converged drop size distribution from all our simulations. And that also ends our part 2. So finally, to conclude, what we can conclude is that contact lines and atomization are very relatable topics because of the singularities, the contact line singularity and the pinch-offs happening in atomization. Now for contact line, what we saw that in this curtain coating setup, there is no universal model to describe all of these type of things. For example, we know that the viscous regime is well understood in Koch's law and Benny solution depending on the range of capillary numbers. Today we have had this curtain coating where the inertial effects played a role when Reynolds number was of order 1. And this was that the foot movement which collapses on a self-similar solution of this 45 degree where you can assume potential flow to be true, and disease transmission requires essentially studying of both contact line as well as atomization thoroughly. Finally, the future scope of this work, the future scope is numerous, but I will focus only on 2 things. Here for contact lines, this is one pulling plate experiment, and you see a corner, a cusp like tip getting developed. This cusp also happens when you do dip coating or you do curtain coating beyond this wetting failure, and this is a 3D effect, and this tip could release some tiny drops, or if you plunge it could release some tiny bubbles that would have very interesting physics. This tip itself would have some very interesting physics. That is of course one study to extend our models to do some 3D stuff to get those type of things. And here you see recently a surface developed by Jiang, Wang, Quéré and others, which contains this conducting material infused with some porous media material. So this porous media material would be sucking the liquid, is super hydrophilic, so it keeps sucking the liquid, and this conducting material provides heat to the liquid. So these type of surfaces can push latent frost temperature much beyond their usual value for water, which is around 500 degree, was pushed to some 1000 degree. So extending our contact line models by adding boiling into them and studying this boiling in porous media is also a possible future scope. And I thank you all for your attention.
Very well balanced between the different parts. I have a general axiom, which is that in principle it's 1 slide per minute or less. In your case, I see 62 here. So you did well, but think of that in the future. Okay. Maybe a way to judge the quality of a PhD is to look at the reviewers. Okay, and so in this case, there is very, very little doubt about the quality of the work, because we have fabulous reviewers, Jens here and Shervin there, international reviewers in both cases. And so the tradition is that we start the question with the reviewers, and the second tradition